Good morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. Today, we are going to discuss about some more properties in the Laplace transformation. We already discussed 4 properties in the Laplace transformation in the last class. Those 4 properties are the linearity property. Second one is a shifting theorem or translation in time domain. And third property, complex translation of or translation in frequency domain, frequency shift property. And fourth one is a differentiation theorem or the differentiation in time domain. And what is the importance in their differentiation in time domain means Laplace transformation, there is a bidirectional Laplace transformation is there and the unilateral Laplace transformation. For bilateral transformation and unilateral transformation, all the properties is similar except differentiation in time domain is only the different property in the unilateral. For bilateral and the unilateral, all the properties are similar except differentiation theorem. What is the difference here? X of s is equal to s into x of s minus x of 0 minus is a d by dt of x of t, the unilateral Laplace transformation. For bilateral Laplace transformation, the d by dt of x of t, the derivative of the time domain function for bilateral Laplace transformation is s into x of s only. Since for unilateral, the limitations is from the 0 minus to the x of t e power minus st dt. The definition of a unilateral Laplace transformation, x of s is equal to is unilateral Laplace transformation. For bilateral Laplace transformation, the x of s varies from the minus infinity to infinity. So minus infinity to 0 and 0 to infinity. Bilateral or two-sided Laplace transformation. It is a single-sided Laplace transformation. X of t e power minus st dt. Here the 0 minus is nothing but just below the 0 and 0 plus is just above the 0. Actually, both are equal to the 0 only. Nothing is a difference, my dear students. The representation of the 0 minus is just below the 0. These are only the difference for the properties for unilateral and the bilateral Laplace transformation is differentiation theorem or the differentiation in time domain. Okay. And these also we already discussed in the last class. So before the class, following my dear students. And coming to the next property, integration property. The integration property also we discussed in the last class. The integration 0 minus to the t f of t dt is equal to fs by s. Fs by the s. The input, if you can take apply the Laplace transformation for the integral of 0 minus to t f of t dt is equal to fs by the s. This is the integration. Always we know the d by dt derivative. Whenever you can apply any derivative, you can take it is a multiplication only. Multiplication. The Laplace transformation of the derivative is s into x of s. The frequency is multiplied with the s. Now the integral 0 minus to the t, here the t, my dear students, not the infinite t value. X of t dt. X of t dt, the Laplace transformation is the derivative x of t is s into x of s. Laplace transformation for the integration of the time domain function in frequency the 1 by s into x of s. 1 by s into x of s. If it is the nth derivative dt power n is a x power n. Okay, and if this is a integral with a 0 to t1, t2, and the last is a tn, can apply the tn times the integral. It becomes of x of s by the s power n. X of s by the s power n. Up to this, in the last class, we already discussed the 5 properties. One is linearity property, and second one is a time shift property, a translation in time shift or translation in time, and complex function, or it is a frequency shift, translation in frequency shift, third property. And fourth property is a differentiation or differentiation theorem, differentiation in time domain. And fifth property is integration theorem. Okay, my dear students. These are the 5 we discussed in the last class. Only there is a difference for the fourth property of bilateral and the unilateral. Okay, my dear students. Now you go for the 6th one, differentiation by the s. We already seen that, we already discussed about the differentiation in time domain. Now it is a differentiation in the s domain. Nothing but is a frequency domain. Let the Fourier transformation of Laplace transformation of f of t is f of s. Then the differentiation in complex frequency domain. Differentiation in complex frequency domain corresponds to the multiplication by the t in time domain. Corresponds to the multiplication in the t for the time domain. Okay, multiply the t in the time domain. There is a differentiation occurs in the frequency domain. Now let us see the differentiation in s domain. 6th property. Differentiation by the s, or in s domain you can call it as s domain or the frequency domain also. Frequency domain. What is the statement here? The statement saying that the d by the ds of x of s in the frequency, the Laplace transformation for this one is a t into x of t. For the t into x of t, you can apply the Laplace transformation. We'll get the differentiation in the frequency domain, nothing but the s domain. Let me go over the proof. According to the definition of the Laplace transformation, x of s is equal to integral minus infinite to infinite x of t e power minus st into dt. For Fourier transformation and the Laplace transformation, here only the difference is instead of s, there is a j omega is there. Instead of s, there is a j omega. The shortcut notation of j omega, x of j omega is equal to x of omega. That is also the x of s. Simple. Wherever the j omega is there, you can substitute the s. It becomes to the Laplace transformation only. It becomes to the Laplace transformation. Following my students. Now, what they're asking here, the differentiation in the s domain. So apply the differentiation on both sides with respect to the s. Yes, with respect to the s into x of s is equal to. Here the s term is only for the exponential value. The remaining is a constant one. E power minus integral minus infinite to infinite x of t. Take the differentiation with respect to the x for e power minus st dt for this function only. and d by ds of x of s is equal to integral minus infinite to infinite x of t. Now what is the derivative of this one? Applying the with respect to the s, d by dt of e power minus st into the s coefficient is a minus t. S coefficient is a minus t. Okay, into dt. You're applying the derivative with respect to the s for the frequency s terms, and e power minus st with respect to the s coefficient is the t, that is a minus t. So d by ds of x of s is equal to integral minus infinite to infinite. Now I am writing the t into x of t as a minus also. T into x of t e power minus st dt. Now you can see here for x of t, apply the Laplace transformation, we'll get the x of s. Similarly, you can apply the Laplace transformation of the t into x of t. Therefore, the t into x of t, the Laplace transformation is d by ds of x of s is a pair. Laplace transformation pairs t into x of t, the d by ds of x of s, the frequency term. Okay. So here, for the Laplace transformation of t into f of t, the minus d by ds of f of s. We are taking the minus here itself, minus d by ds of f of s. By the definition of the Laplace transformation, f of s is equal to, we are taking here the by unilateral, my dear students. Don't confuse. 0 minus to the infinite f of t e power minus st dt. I explained in terms of the x. Here they explain in terms of the f of t and f of s. D by ds of f of s is equal to integral 0 minus to infinite f of t d by ds of e power minus st dt. Okay. Then apply the derivative for the e power minus st into minus t. So minus the Laplace transformation of the t into f of t. So we got it is a Laplace transformation of t into minus t into x of t. Okay, my dear students. Now coming to the seventh one, initial value theorem. It is a very, very important theorem. It is initial value theorem. In this initial value theorem, we are using the unilateral only. Now, whatever here, they are representing the integral 0 minus to the infinite. For initial value theorem, we have to must and should, we have to use the unilateral Laplace transformation only to prove the initial value theorem. Don't use a bidirectional or bilateral Laplace transformation. So what is the statement saying the initial value theorem? It is a limit, not the limit. Laplace transformation of f of t is equal to f of s. Then the initial value of f of t is given as initial value of f of t. What is that initial value? Assuming the f of 0 plus. 0 plus is the initial value. Here, what is the 0 plus means? 0 plus is the just above the 0. 0 and 0 plus and 0 minus. Just below the 0 is a 0 minus, just above the 0 is a 0 plus. So f of 0 plus is equal to limit t tends to 0 plus f of t. That is equal to limit s tends to infinite. So initial value, it starts from the time domain is a 0 plus and s domain is end with the infinite. So initial value 0 plus in the time domain, and in the s domain, s tends to infinite, s into f of s. I have to prove the limit t tends to 0 plus f of t is equal to limit s tends to infinite, s into f of s. Okay. provide that the first derivative of f of t should be the Laplace transformable. We know that the Laplace transformation of the d by dt of f of t is equal to s into f of s minus f of 0 minus, by the definition of unilateral Laplace transformation, or one of the property, the differentiation in time domain. Differentiation in the time domain, my dear students. So now on both sides, if I'm taking the limit s tends to infinite, on both sides, limit s tends to infinite, the Laplace transformation of d by dt of f of t is equal to limit s tends to infinite, the total function is s into f of s minus f of 0 minus. Consider the Laplace transformation of the above equation, that is LHS here. Consider the LHS of the above equation. LHS is limit s tends to infinite. What is the Laplace transformation of the d by dt of f of t? According to the definition of unilateral Laplace transformation, 0 minus to infinite. What is the f of, here this x of t signal is d by dt of f of t e power minus st into dt. So actually x of s is equal to integral minus infinite to infinite x of t e power minus st dt, the Laplace transformation. For unilateral Laplace transformation is integral 0 minus to infinite x of t e power minus st dt. I need the x of t, the Laplace transformation of the derivative of the signal. So x of s is equal to integral 0 minus the Laplace transformation is a d by dt of x of t. D by dt of x of t e power minus st dt. So this is nothing but the Laplace transformation of d by dt of x of t only, or otherwise it is equal to the x of s. Okay. So I substitute the d by dt of f of t e power minus st dt by the definition of Laplace transformation. Okay. When we can substitute limit s tends to 0, limit s tends to infinite here, e power infinite. What is the e power infinite, my dear students, in this function? The total function e power infinite is a 0. You know the e power infinite always is a 0, e power 0 is a 1. So and I'm taking here the limit s tends to infinite, e power minus infinite into t. Substituting the s value as infinite, it becomes of the 0. So LHS is equal to 0. Now you can substitute this 0 value in this Laplace transformation of the d by dt of f of t is a 0, that is equal to limit s tends to infinite s into f of s minus f of 0 minus. Okay, and in the second function there is no any s terms. In the second term there is no any s terms, so you can bring that into the LHS value towards the left side. Here the minus becomes is a plus. F of 0 minus is equal to limit s tends to infinite s into f of s. Now here they are explaining that f of 0 minus indicates the value of f of t just before the t is equal to 0. And f of 0 plus indicates the value of f of t just after the t is equal to 0. If the function is continuous at t is equal to 0, then its value just before and just after t is equal to will be the same. Okay, my dear students, remember this one, f of 0 minus indicates the value of f of t just before the t is equal to 0. And f of 0 plus indicates the value of f of t just after the t is equal to 0. If the function f of t is continuous at t is equal to 0, then its value just before and just after t is equal to 0 will be same. So first f of 0 minus, I'm taking the f of 0 plus. So both are the equal. F of 0 plus is equal to f of 0 minus for f of t is a continuous at t is equal to 0. Okay. Now replace the f of 0 minus, f of 0 minus as f of 0 plus is equal to limit s tends to infinite s into f of s. This equation is used to determine the initial value of f of t and its derivative. Initial value of f of t and its derivative. Got it, my students? It's a very important. Then coming to the eighth property, the final value theorem. See, in the final value theorem, initial value theorem, it starts the time domain is t is equal to 0 plus, and the frequency domain is s tends to infinite. Now the final value theorem is a reverse. The limitations is for limit t tends to infinite f of t is equal to limit s tends to 0 s into f of s. Got it, my students? Initial value theorem. Initial value theorem is f of 0 plus or limit t tends to 0 plus f of t is equal to limit s tends to infinite s into f of s. Now final value theorem, the statement is saying that f of t is a limit t tends to infinite. Here it is a 0 to infinite initial value theorem. Final value theorem starts at the time domain is infinite is equal to limit s tends to 0 s into f of s. Got it, my students? Now you have to prove that limit t tends to infinite f of t. Again, here also you can use one of the property that is nothing but a differentiation property. That differentiation property for unilateral. For unilateral only, there is an addition factor. We have minus f of 0 minus. Otherwise, bilateral is only for s into f of s only. Okay. Now taking the same equation, the Laplace transformation of d by dt of f of t is equal to s into f of s minus f of 0 minus. Now, take the both sides, limit s tends to 0. Limit s tends to 0. It is also limit s tends to 0, my dear students. This is a limit s tends to 0, and this one is also limit s tends to 0 only. There is a wrong is occurred here. Use take the limit of the above equation s tends to 0 on both sides of this equation. So limit s tends to 0, the Laplace transformation of the d by dt f of t is equal to limit s tends to 0 of total function s into f of s minus f of 0 minus. That is equal to limit s tends to 0 s into f of s minus, and there is no any f term here, s terms. Taking the LHS, what we did in the same initial value theorem, you take the limit s tends to 0, the Laplace transformation of d by dt of f of t. That d by dt of f of t using the definition of Laplace transformation, integral 0 minus to infinite, that Laplace transformation is a unilateral only, my students. D by dt of f of t e power minus st dt. Now, here there is a s tends to 0. Here there is a s tends to 0. Now you can substitute s tends to 0 in this equation. E power minus 0. E power minus 0 is a 1. So integral 0 minus 2 infinite d by dt of f of t dt. Derivative of integral, simply the constant of f of t. The upper limit is infinite and lower limit is 0 minus. Okay. And limit s tends to, not the limit. Here you can observe here the f of t is upper limit is infinite and lower limit is 0 minus. Now I am substituting the values, these all infinite and 0 minus is the t values. So f of infinite minus f of 0 minus. Got it, my student? This is LHS. What is RHS we have? RHS is limit s tends to 0. Limit s tends to 0. S into f of s minus f of 0 minus. Okay. Now implies I'm taking this as f of t signal. So f of infinite, let us put it f of t minus f of 0 minus is equal to limit s tends to 0, s into f of s. And here there is a s, I am taking the limitations. In the second term, there is no any s terms. No need of using the limit s tends to 0 because there is no any s terms. So directly you can write as f of 0 minus. In the left hand side, we have the minus f of 0 minus, and right hand side is also f of minus, f of 0 minus is there, it get cancelled. Implies f of infinite is equal to the limit s tends to 0, s into f of s. Now I am writing in the LHS, limit t tends to infinite. Limit t tends to infinite, f of t, because I am substituting the t as infinite here, is equal to limit s tends to 0, s into f of s. Got it, my friend? Why is I am taking here the limit t tends to infinite, f of t minus f of 0 minus. Okay, so there is no any s term, t terms here. So it get cancel off a minus f of 0 minus and minus f of 0 minus. And finally, the limit t tends to infinite f of t is equal to limit s tends to 0, s into f of s. The final value theorem is useful in analysis of analysis and design of the feedback control system. Following, my students. So only you have to remember the initial value and the final value is, it starts from the, is f of t plus 0 means limit t tends to 0 plus f of t. Okay, so initial value theorem and the final value theorem. Initial value theorem is in the time domain is a limit 0 plus, in the frequency domain s tends to infinite. And final value, initial value theorem it is. And final value theorem is here the time domain is infinite and frequency domain is 0. The remaining both the same, f of t and the s into f of s. And these two theorems, initial value theorem and the final value theorem, we can use to prove these equations by using the one of the property, differentiation theorem, that too unilateral Laplace transformation. Okay, don't use the bilateral Laplace transformation theorem. Understood? Now the last 10th property here, the 10th, before that 10th, actually 7, 8, 9, and it is a 10th property only, my students, not the 10th, it is a 9th property. This is a 9th, my students. Okay, convolution theorem. Convolution theorem. So what is a convolution theorem? We already know in the Fourier transformation also. If the time domain is a convolution, the frequency domain is a multiplication. In the Fourier transformation, the Fourier series also. Here also we can take the two signals, f1 of t and the f2 of t, convolute both the signals, then apply the Laplace transformation. In the frequency domain is a product. So if f1 of t is a Laplace transformation of f1 of s is the Laplace transformation of f1 of t, f2 of s is a Laplace transformation of f2 of t, then the Laplace transformation of f1 of t convolute with the f2 of t is equal to f1 of s and the f2 of s. f1 of s and the f2 of s. Got it, my students? So now, using convolution definition, the convolution definition is integral minus infinite to infinite f1 of t, f1 of t, f1 of tau, and the f2 of t minus tau dt. Here they are taking that f1 is a t minus tau and f2 is a tau. Nothing is a difference. I will explain here. Ninth property, convolution theorem. A convolution in time domain. Time domain in Laplace transformation. Okay. The statement saying that if, let us take, I'm taking the x values, x1 of t, with convolute with the x2 of t, Laplace transformation, x1 of s, product of x2 of s. This is a statement you have to prove for the convolution in time domain. Proof. So on the definition of the Laplace transformation, the Laplace transformation of x of t is equal to integral minus infinite to infinite. I'm taking the minus infinite to infinite means bilateral Laplace transformation. X of t e power minus st dt. Okay. What is the x of t? I'm using the Laplace transformation of x1 of t with the convolution of x2 of t is equal to integral minus infinite to infinite x1 of t with the convolution of x2 of t e power minus st dt. Okay. Now use the definition of the convolution. Apply here is equal to integral minus infinite to infinite. Within the bracket, the definition of convolution integral, integral minus infinite to infinite, x1 of tau, x2 of t minus tau, d tau, into e power minus st dt. Okay, I apply the definition of the convolution here. x1 of tau, x2 of t minus tau, d tau. Got it? Is equal to, I'm using the e power minus infinite to infinite, x1 of tau, d tau, and integral minus infinite to infinite, x2 of t minus tau, e power minus st dt. Now see, this is a second property. According to the second property, time shift property is a translation in time domain. Translation in time domain. Here it is delayed with the tau samples. It is delayed with the tau samples. In this equation, that is equal to integral minus infinite to infinite x1 of tau d tau. I'm using the translation in time domain or the time domain property. It gives that e power minus s into the t is tau here, e power minus s tau, e power minus s tau, x of s actually, it is a x2, so it is a x2 of s. Got it, my dear students? You got the definition of second property, t minus tau, or otherwise you can substitute the t minus tau is equal to p, dt is equal to dp, and the t is equal to, you can use the value directly, you get the e power minus s tau into x2 of s only. Again, you can see the integral minus infinite to infinite x1 of tau e power minus s tau d tau into x2 of s. So now see, this is also one of the definition of the Laplace transformation only, but the signal is x1 with respect to the tau. That is equal to x1 of s into x2 of s. Therefore, the Laplace transformation of x1 of t with the convolution of x2 of t is equal to x1 of s into x2 of s. What it matters? Convolution in time domain, product in the frequency domain. Convolution in frequency domain, product in the time domain. That is nothing but a modulation theorem. Is a convolution theorem. Frequency domain is a convolution. The time domain is a product. Got it, my students? The ninth one. So it's the same we got here also. See f2 of t and the f1 of s and the f2 of s. The two functions 0 to infinite, they are taking as a unilateral. F2 of tau e power minus s tau d tau is f2 of s, and f1 of x e power minus s into x d of x is equal to f1 of s. Got it, my dear friends? Totally the 9 properties we discussed in the Laplace transformation. Okay. Now you can write these is also one of the assignment, my dear students. In the second assignment, you can take it as, because it is in the 4th unit, second mid syllabus. Write these also the assignment, the 9 properties totally. What are the 9 properties? Once again, you can go through that one. The first property saying linearity property. And second property saying that shifting theorem or the translation in time domain. And third property, complex translation of the translation in frequency domain. And fourth property, differentiation theorem of the differentiation in time domain. And fifth property, the integration theorem. Sixth is differentiation by S or differentiation in the S domain. And seventh property is the initial value theorem. It is very important, and you have to use the bilateral Laplace transformation for the derivative of derivative in time domain signal to prove the initial value and also the final value. So seventh and eighth is the initial and the final values theorem. And ninth one is a convolution theorem. Ninth one is a convolution theorem, my dear students. Okay. Now you go for the sum of the examples in the Laplace transformation. Some of the examples in the Laplace transformation. Find out the Laplace transformation of an exponential function which is given as f of t is equal to e power at. The above function can also be written as e power at mu of t to indicate that e power at exists only for t is greater than or equal to 0. Since mu of t is equal to 1 for t is greater than or equal to 0. So the given signal is f of t is e power at mu of t. E power at mu of t. Okay, you have to find out e power at mu of t of the Laplace transformation. According to the definition of the Laplace transformation, x of s is equal to integral minus infinite to infinite x of t e power minus st dt. We know this one. What is the given x of t? Here is f of t, my dear students. I am using the x, don't confuse there. So because in some textbooks, they are always using the x values only. Okay. Integral minus infinite to infinite. I'm taking the x of t is e power at mu of t. E power at mu of t. E power minus st dt. And is equal to integral that mu of t can change the value is 1, and the limitations is also changes from 0 to infinite or 0 minus to infinite. 0 minus is just below the 0, or always is a just you can take the 0 only. There is no any difference for the 0 minus, 0 plus and the 0. In the evaluation of to solve the some problems, we have to take only the 0 plus and the 0 minus is both are is a 0 only. Okay, so e power at e power minus st dt. because the mu of t is equal to 1 there. So e power at, take the common of the e power minus s minus a into t dt. That is integral 0 to infinite. And take the minus here. S is a minus and the minus into minus is a plus. Apply the integral for the exponential value. That is e power minus of s minus a into t whole divided by the minus of s minus a, with upper limit is infinite and the lower limit is 0. When I have substituted the upper limit is infinite, it becomes of 1 minus, not the 1 minus 20, so 0. 0 minus lower limit is 0 means the t values 1 and whole divided by we have the s minus a of minus s minus. The minus and minus get cancelled, becomes of 1 by s minus a. This is for the Laplace transformation of e power at mu of t. E power at mu of t. Got it? So here also we got the same thing. The Laplace transformation of e power at into mu of t is there 1 by s minus a. In Fourier transformation, we got it is a e power minus at, e power minus at mu of t is 1 by a plus j omega and a minus j omega. See that a minus j omega and a plus j omega for e power at mu of t. The Laplace transformation is 1 by a minus j omega. The j omega is nothing but s here. Okay, yes. But 1 by s minus a and 1 minus s plus a, like that. Got it? We come to the next example. See, before going to the next example, you can see for s is less than a, the Laplace transform cannot be calculated. So s minus a. So we got the s minus a, the region of convergence. Take the denominator and a greater, keep that is a greater than the 0. S is greater than a. This we can call it as a region of convergence, ROC. A region of convergence, my dear students. For S is less than a, we got this S is greater than a. For S is less than a, the Laplace transform cannot be calculated since the integral is unbounded. For S is less than a, the Laplace transform cannot be calculated since the integral is unbounded. Therefore, the region of convergence is S is greater than A. Greater than A means exists. Simply we can say for S is greater than A values, the region of convergence is exists. The shaded area shows the ROC. See, this is a spline having the spline with the real axis is a sigma and imaginary axis is a j omega. We can call it as a S-plane. The 4 quadrants. In that 4 quadrants, 0 is origin, and I'm taking is the S is equal to A. So because it's a greater value, A it is A. Above the A value, the total is a region of convergence. The shaded area what we have here, above the A. Because therefore the region of convergence is S is greater than A. The shaded area shows the ROC. Is ROC. ROC is S is greater than A, region of convergence. Thus the Laplace transformation pair is e power at mu of t. The Laplace transformation is 1 by S minus A, and the region of convergence is S is greater than A. S is greater than A. One-sided. It is a one-sided, that too positive sided. Positive sided. Remember here. Why we are got the greater than means here the mu of t is in the positive sided, my dear students. If this mu of t is changes to the negative sided, then the shaded area will get in the left hand side. Now we got the shaded area in the right hand side. The region of convergence is above the value of S is greater than A, not equal to actually, it's S is greater than A. Above the A values, for all the values of above the A, it is exists. Okay, exists. Region of convergence. Remember that. It is very important. You have to remember, without the region of convergence, we can't apply to find the inverse Laplace transformation. Laplace transformation we got. They find the inverse Laplace transformation by giving the region of convergence. So without the region of convergence, we can't say for 1 by S minus A, what is the inverse Laplace transform? Because 1 by S minus A will get the two for the two functions. E power at mu of t will get the 1 by S minus A, and e power at mu of minus t minus 1 also 1 by S minus. So there is ambiguity we will get. So without ROC, we can't say which is the inverse Laplace transformation of 1 by S minus. Okay, so definitely you have to know which is the shaded area and which values there exists. Got it? So coming to the second example, you can see for the second example, find the Laplace transformation of the step function. The step function, the Laplace transformation. So minus infinity to infinity, I got the definition, x of s, the integral minus infinity to infinity, x of t, e power minus s t dt. So what is the x of t? Step function. So integral minus infinity to infinity, mu of t, e power minus s t dt. What is the mu of t? The value is 1 from 0 to infinite only. So e power minus s t dt. That is equal to, apply the integral, e power minus s t by minus s. Upper limit is infinite and lower limit is a 0. By substituting the upper limit, the value is a 0. Substituting the lower limit, the value is a minus 1 and minus s. So minus and minus get cancelled, you get the 1 by s. So the Laplace transformation of the mu of t is equal to 1 by s. Got it? So mu of t is equal to, the Laplace transformation is 1 by s, my students. So these are all the bits all. You have to remember that one. What is the Laplace transformation of e power at mu of t? 1 by s minus e. You get the asking in the online. These are the bits, some of the bits. By using the definition of the Laplace transformation, you have to derive or you have to solve the e power at mu of t. What is the Laplace transformation? And what is the mu of t? The 1 by s. Next one. Third example. Find out the Laplace transformation of the ramp function. Ramp is nothing but r of t. R of t is equal to t. R of t is equal to t. The t is greater than or equal to 0. Ramp is nothing but the linear function. Linearly. So as the t is increases, r of t is also increases linearly. So therefore the r of t is equal to the t for t is greater than or equal to 0 up to the infinite. Okay. Now you can find the Laplace transformation of the ramp function or the linear signal. Simply you can say linearly. Now this is from the t into mu of t, because the t into mu of t varies from the 0 to infinite. We got the definition of the Laplace transformation. X of s is equal to integral minus infinite to infinite x of t e power minus s t dt, and that is equal to integral minus infinite to infinite. Now I'm taking the x of t as a ramp function. So t into mu of t. Why it is multiplied with the mu of t? Because it is varies from the 0 to infinite. Got it, my students? e power minus st dt. Mu of t changes the limitations here, the 0 to infinite, t into e power minus st dt. Now I can, by using the by parts integration by parts, the t into, apply the integral for this one, e power minus st by minus s minus, again the integral, take the derivative of t, 1, apply the integral for this one, e power minus st by minus s into dt, and the limitations is from the 0 to infinite. Again that is a t e power minus st by minus s. Apply that, again the integral of e power minus st. So you have the minus into minus is a plus, e power minus st by, for this e minus s, again we'll get the s into s is a s square minus s square. So this minus will get here itself. Got it, my dear students, for the minus. So apply the limitations of the infinite and 0. First of all, if I am applying the infinite, e power infinite is a 0 and e power infinite is a 0. First two terms becomes a 0. And lower term you can apply, the first term is a 0 because it's a t. And the last term what we have here, e power minus s into t, that t value is a 0, 1. And in the denominator there we have s square. Because we are substituting the lower limit, there is a minus will get, and here also minus, both are, it is a plus. Once again I will explain. First of all, if I am applying the infinite, the t into e power minus infinite by minus s plus e power minus infinite by minus s square for the infinite. For lower limit, minus of, and here it is a minus is there, now the plus t is a 0, 0 into e power minus 0 by s, and here also the minus is there. For the lower limit, minus will get plus e power minus 0 by s square. So e power infinite is a 0 and e power infinite is 0, 0 into anything is a 0, and e power 0 is a 1, 1 by s square. See the Laplace transformation of the ramp function, the t into mu of t is a 1 by s square. For step function is the Laplace transformation, mu of t, Laplace transformation is 1 by s, t into mu of t, Laplace transformation is 1 by s square. Suppose here that 1 is there, the t into mu of t, the t square by 2 mu of t, it becomes of the Laplace transformation is 1 by s cube, and t cube, this is a factorial, my dear students, 1 factorial will get t cube by 3 factorial, nothing but the 6. Mu of t, the Laplace transformation is 1 by s power 4, and so on. Got it? So the nth derivative, nth value, it is a t power, here the 3 plus 1, that is a 3 here and the 6. So means the t power n by the n factorial with the mu of t. What is the Laplace transformation by observing this? The t into 1 factorial, t square by 2 factorial, and 3 factorial, and so on, 1 by, here the t is t power 1, s square is 1 by s square n plus 1. So here the n value is there, that is added with 1 on 3. We can take the 3 plus 1. So t power n factorial, t power n by n factorial mu of t, the Laplace transformation is 1 by s power n plus 1. Okay, generate. If the slope of the ramp is k, then it is given as f of t is equal to k into r of t, or the k into t. The Laplace transformation of the function will be k into r of t is a k by s square. Simply we can multiply the k here because amplitude is there. R of t is nothing but k into t mu of t. We know the t into mu of t is a 1 by s square, and k is multiplied, we'll get that k by s square. What it? And if it is a shifted delayed function, r of t minus t naught is equal to t minus t naught, and r of t minus t naught Laplace transformation is e power minus s into t naught. This is about the definition of, not the definition, one of the property, shifting property, time shift property. Multiply this one, e power minus s into t naught by s square. If k into is there, k into e power minus s into t naught by s square. Got it? Any confusion, my dear students? Here, there is no any confusion. See, x of t minus t naught Laplace transformation is e power minus s into t naught x of s. What is the x here? The ramp r of t minus t naught. The Laplace transformation is e power minus s into t naught. For x of t, the Laplace transformation is x of s. For r of t, the Laplace transformation is by s square. Something same. The r of t minus t naught, the Laplace transformation is e power minus s t naught by s square. Got it? If it is a k is multiplied, you get the k into e power minus s t naught by s square. We got another formula, the Laplace transformation of the ramp function 1 by s square, the Laplace transformation of step function 1 by s. Okay, the Laplace transformation of a delayed version of the ramp function e power minus s into t naught by s square. The Laplace transformation of e power at mu of t 1 by s minus e. Okay. Now the fifth another example, find out the Laplace transformation of sine wave. A sine wave is given as a into sine omega naught t. We know the sine omega naught t in terms of exponential 1 by 2j e power j omega naught t minus e power minus j omega naught t. What my students? Assuming that it is f of t. So f of t is equal to a by 2j e power j omega naught t minus e power minus j omega naught t. Substitute the Laplace transformation in this. The Laplace transformation of e power j omega naught t minus the Laplace transformation of e power minus j omega naught. We know the Laplace transformation of e power at. At is 1 by s minus a. Instead of a, here the j omega naught. J omega naught. The first one we can see. First one, the Laplace transformation of f of t is equal to, using this property, using this Laplace transformation, that is a by 2j full multiply for this e power j omega naught t, a as j omega naught. So 1 by s minus j omega naught minus, here what is a e power minus j omega, 1 by s minus of minus j omega. Okay, a value is, that is equal. Simply we can say the Laplace transformation of e power minus at mu of t. Laplace transformation is 1 by s plus a, my dear students. Remember this one. I use here it's one. So a by 2j, it is s plus and s minus. So s plus j omega naught minus s minus j omega naught. It becomes of j omega naught. Whole divided by a plus b into a minus b, s square minus j omega naught whole square. Now s and s get cancelled. J omega naught and j omega naught is at 2j omega naught. 2j is also get cancelled here. In the numerator, we have only the omega naught. So a into omega naught whole divided by j square, we know the minus s square plus omega naught square. So sine omega naught t, a into sine omega naught t, the Laplace transformation is a into omega naught by s square plus omega naught square. Remember this one. A into sine omega naught t, the Laplace transformation is A into omega naught by s square plus omega naught square. Got it? In similar fashion, the cos omega naught t also. What is the formula for the cos omega naught t? Here the plus. Plus, and here also the plus, here also the plus. Now simplify with the plus j omega naught and j omega naught get cancelled. 2s will get. 2 get cancelled, and it becomes of there is no any j in the denominator also. What is a Laplace transformation of A into cos omega naught t now? By changing only the plus here. Laplace transformation, whenever I am using the plus here, it is also plus. After simplification, it is a plus. 2s in the numerator, and j omega naught and j omega naught get cancelled. There is no any j in the formula of cos e power j omega naught t plus e power minus j omega naught t by 2 only. 2 to get cancelled. It becomes of A into numerator is a s by denominator is the same, s square plus omega naught square. A into cos omega naught is A into s by the s square plus omega naught square. Only simple remember here, cos will get numerator is a s, sine will get numerator is a constant, omega naught is a constant. Variable is a function is a s. Got it? Okay. The Laplace transformation of sine function and the Laplace transformation of cosine function also. Cosine function is numerator is a s, denominator is as usual, both are the same. Got it? So the Laplace transformation of A into omega naught by s square plus omega naught square. Similarly, e power minus at cos omega naught t is another way. Another one, it is not the same, but it is a multiplied with e power minus at, not the a. A into cos omega naught t is a into s by s square plus omega naught square. But e power minus at into cos omega naught is a different matter. Okay, that we'll discuss in the next class. So any doubts? Any doubts, my dear students? Okay, thank you.